This now I realize that I could have done it better probably and make this instead of updating the money after each product update, I could update the money after each bill update because that's the same thing and it happens in a single thread. So that would avoid locking and unlocking the money this much. But other than that, yeah, it should be fine.
Okay, go on.
For the inventory, for each bill, I also have a read lock. I do this because basically I want the bills to be processed at the same time, so concurrently or in a parallel way. I want to be able to have two threads processing bills at the same time. And then for the make inventory function, I do a write lock because I want it to be separate from all the others. So I want to do the inventory while no other bills are being processed. And this is a way I thought about doing it. So this is just to make sure, because also in the threads, when I process the threads, I do something with, as you can see, quite some atomic variables and the barrier. Basically, I have a barrier that's counting how many threads came to it. You see it initialized to the number of threads plus one, which is the inventory maker. And first the inventory maker is running. It shouldn't stop because this is initialized to false. Or sorry, it should stop from the start probably. Wait a second. I forgot what I've done. So should stop is initialized to false. Okay, so this should go in. But then it shouldn't do the inventory because it is initialized to false. And it waits on it. So the inventory checker stops from the start, and then the workers are doing their job until this if is available. So until a worker reaches its fifth item scanned, or from 5 to 5 items, it reaches this if. It increments an amount of waiting threads. This is also an atomic variable. It's an atomic int. It sets the do inventory to true. And then it waits. It notifies the inventory maker. This is being notified continuously, let's say, but it won't continue. It won't basically do the inventory until all of these.
Just a moment. Do inventory, what type does it have?
It's an atomic bool.
And is there a function called wait?
Yeah, so on atomic variables, you can use them as conditional variables, and you can wait for those to change their.
Okay. Does it a busy wait behind?
Yeah, it's like a conditional wait, but without a mutex.
Mm-hmm. Okay.
And in here, the notify all is only called when the waiting threads, when the number of waiting threads is equal to the number of workers, basically. So only when the last worker gets to this if will it call notify all, and then it means that, yeah, of course, no bills are being processed anymore. So the inventory will start doing its job. It will set back the do inventory to false, and then it will notify the workers in here, which are waiting for this do inventory variable. It will notify them all that, okay, I'm not doing the inventory anymore, and you can do your job. It's a little bit counterintuitive how these atomic Boolean waits work, because as you can see, in here at least I pass a true, but inside you have to pass the old value. So the value that you want not to be inside of the variable when you come back. So in here I'm saying that, yeah, I wait for this to not be a true. So I want it to be a false in order to continue.
Okay, good. What I wanted to see is the prevention of race conditions. And you did it via the mutexes on each product type and the mutex on the amount of money.
Yep.
And also, could you please explain again the read-write mutex, the usage of the...
That read-write mutex is used especially for the workers and inventory. It's just like I want the process build function to be able to work in parallel, but I want this one to work in parallel with any other function. So this one I can only have on one thread running. These ones I want to have in multiple threads running.
Okay. For the rest, for the synchronization of the threads, what I expected was simply to launch all the threads and let them run as they are scheduled, and see that due to the synchronization mechanisms that we have the correct result in the end.
Oh, yeah.
And that would have been enough.
Yeah, I wanted to do this as well, just to work with these kind of things because I never did them in C++. That was the way I did it in the beginning, but I noticed that the inventory would run very few times or no times at all. Or it would, or sorry, it would run only one time, which is at the end. So it would, yeah, it just wouldn't get processor time.
Okay.
So
good.
That's why I wanted to make it run each 5 products, let's say, or each whatever number of products.
Okay. Thank you.
And if I run it, it should hopefully work.
Oh,
so
yes.
Yeah. It prints all good. That means that the inventory returned the true. So it's the inventory, where was it? So it returns true if the price of all the bills that were processed is equal to the sum of money in the shop. So it was counted correctly, basically, and the false if it was not.
Okay. I will take back the screen. Yes? Sorry.
Oh, no, I just said sure.
By the way, I was looking at the wait and notify one, notify all. It seems they are relatively new additions in C++ 20 standard. I'm a bit surprised that they added such things, because I assume that the underlying implementation is a bit harder to achieve, but well, since they did it. Before moving on, let me call the attendance. So I will call each of you and please tell if you are here. I will read from the list from the last week. So Badiu Bogdan. Okay. Bădăruță Bianca. Bădăruță Bianca.
Yeah, I'm here. Sorry, yeah.
Okay, thank you. Balázs Hazi Alex, is that correct?
Yes, that is correct. I'm here.
Thank you. Balint Flaviu. Balint Flaviu. I cannot hear. So I assume it's missing. Albu Flaviu.
Da, aici.
Okay. Alexandrescu Andrei.
Here.
Thank you. Andreica Daniel.
I'm here.
Thank you. Barza or Bârzu?
Barzu.
Barzu.
Yep.
Okay, thank you. Plus the lab. Bodica Septimiu.
Here.
Thank you. Catrinei Raul.
Here.
Thank you. Babei Denisa.
Aici. Prezentă.
Thank you. Birtocean Ada.
Prezentă.
Thank you. Just a moment. Borlea Mihai.
I'm here.
Thank you. Anyone else?
Yes, me, Avram, Gheorghe.
Avram Gheorghe.
And me, Flaviu Balean.
Baleanu Flaviu. Baleanu or Balean?
Either way, but it's with A.
Okay. Good. Anyone else with questions or who wants to show us?
Yes, I solved the second problem with the bank accounts.
Let's see it.
Okay, so I modeled the problem like this. You have there is a bank containing a vector of accounts. Each account has some balance and has a log of transfers of operations. And I used to store these vectors, I used the vector safe, which is a wrapper I wrote over the vector class, because I had some issues with while pushing at the same time in a vector, so I did this type of locking. I hope this approach is okay. Okay, in the main program, I create a bank, I create n accounts, I create a thread for each account, and inside of a thread, which is this function here, for each account, I perform a number of transfers. So I think it's 50 right now. And a transfer means choosing another random account, choosing a random quantity, how much to transfer, and transferring them, calling this function. Now, this function is obviously in the bank. The bank has the transfer, receiving the ID of the account where the transfer is from, to, and the quantity. And here would be the critical region we are interested in, when you remove funds from one account and you add funds to another account. And this is where I added the logs. I have a mutex over the bank. I think I forgot to mention that. And I use this to make sure that there are no concurrent issues. If I run the program real quick, in my main program, at the end I have this final audit check, which performs a final check at the end, and it's how it's supposed to be. And it also tells me how much time it took. Now, if I remove I think this is also of interest. If I remove these logs, then sometimes it works, sometimes it doesn't work. And I guess the reason is because of the concurrent issues. Okay, now it worked. If I increase the number of accounts, I think, okay, that's not the issue. I was wrong. So let's, I had another issue. I'm not sure if this is relevant because the problem says here to perform some additional checks. So this part here, if the amount of money corresponds with the operation records, and if you have an operation in one account, you should have the opposite in the other log of the other account. And I did those operations, but for some reason, if I remove the mutexes, the program crashes, and I guess it's because of concurrent issues, because it does this concurrent checking. So I had to add another log over these checks to make sure, but that's why I'm not sure if this is required. So what is your input?
First of all, the solution with the global mutex for the whole bank is correct, not very efficient. The second thing, well, it's not very problematic, but I would have expected the threads to be independent of the accounts. It's okay as well the way you chose. Maybe it's a bit harder to have to show the race conditions with your approach because you won't have collisions on the source account with your approach because the transfers that start from the same account are serialized on the thread corresponding to that account. So you will never have conflicts on the first account, only on the second one. One more thing, could you show a bit the account structure?
Yes, so they have an ID, initial balance, which I use for checking if the operations from the log correspond to, I mean, they lead to the same, the current balance, and this vector safe of logs.
And the log, I also didn't watch for it actually. It contains all the operations concerning that account or only in transfers or only out transfers?
So it contains both the ins and outs. An operation has a type and it can be add or remove, but it has only for itself. For this account, for the other account. So for the recipient, I think it's in the other account. That's why I have a transaction ID which is common with the counterpart account. So they have a unique ID globally and one transaction, so I can match two operations in two different accounts.
Yes, that's very good. The log itself, I guess it's mainly protected, or it's also protected by the mutex in the vector safe.
Yes, because I had the same issues. If I use a vector as a data structure, pushing back at the same time is problematic.
But it should work if you have a bank level mutex and the adding to the log is also done with the or under the global mutex.
So adding to the log is done under this bank mutex. And what do you mean should work?
So if that mutex is locked there and unlocked at the end, and between the lock and unlock, it's the place where you add the operation to the log, then
Yes.
you should be able to get away with
I see.
ordinary vector. The mutex is on the level of the bank itself. Is that correct?
Yes.
No? Oh.
Yes, I added these because I thought that if we do not lock this critical region, the program should still run. So that's why I tried to fix it and make it run without these locks. But yes, you're right. If I lock here, then nobody else will push back at the same time. So I can get rid of these.
Okay. On the other hand, part of the goal was to be able to parallelize a bit the operations within the bank. So with bank level mutex, we are back to a global bottleneck with a single thread, effectively a single thread processing all the operations. We can have as many threads as we want, but a single one will perform the bank operations. And part of the goal of this lab is to see how to improve a bit this. We still need some bottlenecks, but we can relax a little bit the things. So the mutex that you put on the vector that contains the log is then needed, and it's done in a good way. Probably you can use or move that mutex at the account level and do under that mutex both the incrementing or adding the funds or removing them. So the two operations there should both happen under the account lock. And this means that they are done in sync atomically. If an operation appears into the log, then it's also reflected on the balance of the account. And we have a fine granularity in that operations on independent, on distinct accounts can go in parallel. They don't hit a global mutex. They are protected by distinct mutexes because they are distinct pieces of data.
I understand. Yes, it's way better to do that. Okay, then I'll modify it and present it again next week, if that's
Good.
okay.
Good.
Thank you.
Thank you also. The second part is, let me share back the screen. So your colleague did an excellent start there. Here is a sketch of what I had in mind with the transfer. Of course, there are many solutions for that. And here is the main part. And we have something like this. Let me go back to the I will add here a file so that I have take advantage of highlighting and so on. Include or text. And let's say mutex as well. And here was a comment that I was making with your colleagues. And it's not shared log, it's something else. Log shared. That's a bit better. Okay, so it's only a sketch, it's only a snippet. And this is one way of dealing with the things. So we have the balance on each account. We have, when we do a transfer, we have to check the balance on the source account to see that we have enough money to perform the transfer. And we do the actual transfer. I didn't put here the log update, but here goes the updating of the log before unlocking the mutex. We have exclusive access to the account, and we have a mutex associated to each account. So no two operations can go in parallel on the same account. They don't mess up with each other, while distinct accounts can proceed independently. And then the problem is what's happening here? Some kind of a warning. Here is what the audit function should do. Now, again, the code is incomplete, but the basic is this part that adds the balances for all accounts. And so this is the second level problem. And it is this one that if you go with that was the original stuff. So we lock the source account, we do the operation, we unlock the source account, we lock the destination account, we update the balance, we unlock the destination account. Please ignore the log shared part. Now, the problem is that if we want to do an audit, and if it happens then that the audit happens while some transfer is going and it is here, the execution of the code in the transfer function is here, then there's no way to find the money that are in transfer because they are already subtracted from the source account and are not yet added to the destination account. So the audit function will not find that the money that are in transfer. The sum will be less that value. And so assuming that, let's say, we do something like we lock the account here and unlock it after adding it to the sum. And there are two solutions for solving this problem. One solution is to use a shared mutex. Anyone knows what a shared mutex is? and how it is used. Anyone wants to say about that? Yes, please. Septimio?
Sorry, my hand is raised because if there's time, I can also present my solution if it's okay.
Ah, okay. Then I'll ask a bit later about that. So about the shared mutex.
It's a mutex that can be locked by multiple threads.
Yes.
And yeah, as the name says, it can just be locked unless there is a unique lock that's already holding that shared mutex.
What's the context of this? Could you tell us a classical problem that has the shared lock as a classical solution? It can be used here, but it's a bit backwards.
Like, let's say a problem that involves multiple readers and a single writer. Using a shared lock would allow you to lock the readers with using that shared part. And when the writer wants to update the data, he can use the unique lock. He can lock that lock only for himself, and the other threads won't have access anymore to getting it shared in a shared manner.
Yes. So indeed, we have readers and writers. And the basic thing is that the readers are compatible with each other. We can have any number of readers reading at the same time because they are only reading. But a writer is incompatible both with other writers and with the readers. A writer and the reader cannot do things at the same time because then the reader will see inconsistent data. We'll see some data that is unmodified, some data that is half modified by the writer, and so on. And so shared mutex has two operations. You
mean lock, shared, and lock? And
yes.
Unlock, shared, and unlock.
And as the name lock shared says, it means that any number of threads can do shared lock shared at the same time. And that's incompatible with the lock, which stands for the regular no, it's called not shareable lock, yeah. Regular lock. Exclusive, yes, exclusive lock. So lock shared is the reader's lock and the regular lock is the writer's lock. Now it's a bit backwards because we should do something like G lock and here G unlock. The audit function is read-only. It only reads the accounts, and it would use the exclusive lock, and the transfer would use the shared lock. It's a bit backwards, and indeed, it has a, let's say, performance problem because it prevents two audits from running at the same time. The goal would be to prevent an audit running at the same time as a transfer and allow transfers to run at the same time as well. Another solution would be to get rid of the shared lock and instead use the lockings on the accounts and interchange those two lock-unlock operations. So now both mutexes are locked here. So we lock the destination just before unlocking the source. And we'll see, so I should have said spoiler alert, we will see why this solves our problem, while it creates a second problem that we have to solve as well. And now another question for you. Do you guess what the second problem is? What happens if we transfer from account A to account B, and we do a transfer from account B to account A as at the same time?
We encounter a deadlock.
Yes, we can encounter a deadlock. It may happen that the first transfer locks account A, the second transfer locks account B. The first transfer reaches here and tries to lock account B as well and stops because account B is already locked. The second thread reaches here and wants to lock account A, and it stops because account A is locked. And now the two threads are in a deadlock. Each of them needs the other one to do some progress in order to for it to acquire the needed mutex and go on. There is a solution here to always lock the accounts, let's say, in increasing order of their IDs or in decreasing order of their IDs. We'll discuss this later. It is a solution, but it starts to complicate the things. Okay. Let's see. Let's see the other lab. So, Septimio, if you want to present us.
I'm sharing now.
Yes.
Okay, first I should show these model classes, account and transfer. And this
So just a moment, let's see a bit the account. So we have the ID, the value, which I suppose is the amount of money in the account.
Currently, yes.
A log of operations and the mutex. Good. And the transfer.
The transfer. Source and destination accounts, the transfer ID, the amount, and a string describing the state.
Something like successful or failed?
Yes, or in progress.
Okay. An enum would be good for that purpose. But that's another story.
Yes, this is C++ 14. And this executor is basically the bank. You can see also the vector of balances. This is created initially with initial values. When I call run, that's the main method. First thing, I need to create a transfer schedule, which is a plan of transfers, all of the simulated transfers, 3000 in my case, and is the number of accounts. So these are parameters. I store the accounts here. please notice this pointer. So I keep passing this pointer throughout the application. The transfer schedule, eventually I pass it to this run transfer schedule threaded. So I'm going there. These are now arguments. I have a pool of threads, and I try to, actually I do split the number of transfers, the scheduled transfers, into a ratio with the number of threads. And for each of these begin and end intervals, I create a thread with the worker that processes that batch. This is how the constructor of the thread looks. It looks like this because I am passing the worker from the same class. This is the
Yes,
function,
so
the worker
it's
function.
pointer to the function to be run, and this pointer, and then all the arguments.
Yes, I have this. This is necessary. And I'll go back to the worker. So I have the start and the end of each batch per thread. This data parameter is used to decide how frequently I do the integrity check.
Mhm.
This is a block with no statement because I'm using lock guards, which are mutexes that have a lifetime corresponding to that block.
Good.
You can see that it's not the most granular solution because for the transfer, I have the mutex at this pretty high level.
Go back a little bit.
Okay.
Where you had the transfer and the mutex.
Transfer range.
So you, no, before, where you call this function, I guess.
Okay, I'll try now. I call the.
Okay, so you create a lock guard over a mutex that is at the bank level. Is that correct?
Yes, if I recall correctly, this transfer is inside this class. Yes, it's this method.
So the thread executor, it's maybe a misnomer because it's the bank. You
Yes.
said this earlier. So you have a global mutex at the bank. And then, of course, everything that happens during the transfer is protected by that global mutex.
We can find some mutexes in the account where the actual transfer logic is, but it doesn't replace this. I mean, I think if I remove this, I'll start getting the integrity errors. I can go to this account transfer logic.
Let's go and see.
Okay, this is also a mutex that I'll comment.
But this is at the account level.
Yes.
Now. Why do you call it cout mutex?
It's a misnomer.
Okay. Anyway, let's see. So you check the balance. So if this is the account, so the then condition is when you have enough money.
Yes.
And destination set value, destination get value plus value. Now, the line 20, I guess, is a problem because you need to lock the destination mutex, the destination account mutex. And similarly, line 23. You had the mutex locked for this operation, but this doesn't go well in protecting the destination mutex. The destination mutex can be accessed from different places.
I have a question here. If there were exceptions that could occur, I would do some error handling in the try catch inside the mutex.
So if you have an exception thrown,
for example, the set value.
yes. If it throws an exception, well, you handle it where it's the right place. But if it gets out of the scope where the mutex is taken, and you have a lock guard or a unique lock or something like that, then the mutex gets freed. Now, whether this is a good thing or a bad thing, it's up to you. So indeed, the lock guard and a similar and a bit more flexible construction called unique lock releases the mutex if the execution goes out of the scope, whether it's by a return, a break statement, or via throwing an exception.
I see.
Of course, you have to be careful that when you release the mutex, you are indeed in a good state.
Okay, then I need to fix this locking here. Maybe I should do this for the next week.
Yes. So I will take back the screen.
Thank you.
So you can organize in several ways the code. Here, it's only a sketch and it's assumed to be a function in the bank or something like that, that's external to the accounts, but it has access to the internal members of the accounts. And the way to go is lock, do whatever we have to do with the account, and at some point unlock the account. And whichever way you go, you have to have something like this. If you have an account level mutex, then you have to have something like this. And it will be a longer story about why overlapping the mutexes solves this audit problem.
Well, basically, it's because nobody can get. If someone gets a mutex, then it will get the other one as well. So that's a nice. That's a nice idea.
What do you mean if someone gets a mutex, gets the
Like
other one?
During a transfer, let's say you have a transfer from A to B and another one from B to A at the same time. Then if one transfer gets the first lock, then it will for sure get the second one as well, because the other lock cannot get the second one since they are interleaved like this.
They cannot cross in the middle if that's what you have in mind. Unfortunately, they can deadlock.
Oh yeah, they can still deadlock, yeah.
As it's written here. But the goal of having this overlap is that we don't allow the audit to get in here. And it's a bit of a tricky thing why this goes well. So it's a good idea to have at least semi-formal proof that we are doing right. Because the thing is, the audit can go somewhere here and see the balance of the second account before being modified. Or it can go here and see the first account after having been modified. And well, it's a bit of seeing exactly what's happening here to show that this doesn't actually happen, or that if it happens, it doesn't harm. Anyway, there is something else I want to show you. Just a moment. So if you write some programs, then at least for this lab, I didn't say much about the main function. And indeed, the way the main function is supposed to go is to create all the threads, and each thread does a number of operations, and then the main thread joins all the created threads. And you can also print some statistics. For instance, here is the way to compute the needed time. With C++11, you have this chrono system clock now that gives you the time now into a variable of time chrono system clock time point. And you do the same at the end. And then you subtract begin from end, you get a duration, you do a cast, a duration cast to some time units. You can put seconds, milliseconds, microseconds, whatever you want. And you have a count that's an integer that says how many such fractions of a second. You can also put seconds there. And here, for instance, is a demo for showing, well, each thread adds how many times? I guess 1,000,000 times. Increments a global variable 1,000,000 times. And we create 16 threads, and we wait for all of them to finish, after which we print the sum and also print the use time. So let's see first what happens with the regular uint64. By the way, we are in release mode, 64 bits compiling. And what's a bit surprising, do we have, how many zeros do we have here?
It's 100 million, so it's 8
A hun-
rows there.
100 million. What's interesting here is that it's a number that's larger than what we expected. We start from 0. We have 16 threads, each of them incrementing it 1 million times. So we expect 16 million, the value. And what we get is 100 million. I have no real explanation for this result. What's even more interesting is that if we compile to 32 bits and we run the same code, I pressed the debug button, not the run.
You can stop it by pressing the red square near continue.
Yes. It's slower and I don't remember how much slower it is. Okay, let's stop it. Let's say Control F5. What's this square? It's the same thing. Something is wrong here. Something is very strange. Oops. Let's go to debug mode. Build, oops. Oh, I had this code. Let me comment it completely. Same value. Oh, wait a minute. I was playing with something else. So everything that you've seen was another program. Now let's see. That's better. So we have some quite random value, 1.5 million approximately, and at least it's quick, 70 milliseconds. And this is in debug on 32 bits. Build solution, and it's a bit quicker on 64 bits. And it will be even quicker in release mode. One millisecond, it says. And now we have a round value here of 7 million. Let's go it again. Interestingly, the same value, but it's wrong. Now, there are two ways of solving the problem. With a global mutex that we lock and unlock on each side of incrementing the variable. Now we do get the correct value, so now it's 16 million. but it takes 1.5 seconds, more or less, in release mode on 64 bits. And we can also use atomic variables. And it's about 10 times faster. It's 141 milliseconds. Build it again and again. So again, the 16 million, the correct value, and 140 milliseconds. It's a good idea also to run several times your program so that you can see how much variation do you have in the running time. You can also go with a different number of threads. Now, for something as simple as that, if I put a single thread and make it do all the work, you'll see that it is faster, less than half the time. But that's because the actual work is kind of bottlenecked because of what's happening here. And this is also motivation for when we do the actual parallelizing thing, to see how to optimize the parallelization so that we can take advantage of the multiple processors. So we don't have but very little concurrency, actual concurrency in the code. So most of the computations should be independent on each thread. Okay, so I guess I'll put somehow this small example on the web page. But until then, please tell me if you have any comments, questions, or anything to show.
Why are atomic variables faster than using a mutex?
So first of all, I don't know all the gory details of that. Atomic variables are implemented in hardware in the sense that there are special instructions. Actually, in most cases, you put a prefix in the operation code that tells the processor that this operation is to, well, involves a variable that can be shared between the threads, and the processor must obtain exclusive access to that variable. Now, the protocol of obtaining exclusive access means going across all the caches and invalidating the caches and so on. This is why it's slow. It's slower than accessing a regular variable. Now, with the mutexes, here I don't have all the details how they are implemented. As far as I know, there is a mechanism involving also some atomic variables, so also some special instructions to see if there's no other thread holding that mutex. And what I don't have the details is exactly the decision that's made if the mutex is held by some other thread. Because somehow you have two possibilities, and probably there is some kind of guessing which is best. One of them is to do a spin wait or a busy wait, So do a loop until hopefully the mutex is freed. The other possibility is to escalate to a mutex that is implemented at the operating system level. And that involves a system call that is a very slow thing. It's something on the order of hundreds or thousands of operations. And when you get there, the things are really very, very slow. And
okay, so basically atomic variables are actually implemented in the hardware, and that's why they're faster.
yes. Also, the mutex is depending on the contention, on how much concurrency is really encountered in the usage. So my bet is that if you have mutexes, but it's very, very rare that a mutex, some thread tries to lock a mutex and find it's locked, I would guess that it's as fast as with atomic variables. You don't pay a penalty at all, or almost at all. I don't know the exact mechanism of implementing the mutex. Well, indeed, even that may be a bit slower, but it's still implemented in hardware. Okay, since we are here, the thing is, here is the page for atomic variables. And the most powerful operation that you have there is this compare and exchange operation. Compare and exchange, it's applied on a variable, and it takes basically two parameters, the expected value and the desired value. And what it does is it compares the current value of the atomic variable with the expected value, and if they are equal, it sets the atomic variable to the desired value and returns true. If they are different, it does nothing and returns false. And with such a thing, you can implement, for instance, the mutex. You say something like, the mutex contains an atomic bool, and you do compare and exchange. You expect it to be false, that's unlocked, and the desired value is true, that means locked and locked by ourselves. Or even better, you have a current owner, some integer value, the ID of the thread, and you expect it to be, let's say, 0 or whatever you have for no owner currently, which means the mutex is free, and the expected value is the ID of the current thread. And you execute this compare and exchange, and if it returns true, it means that you successfully locked the mutex. If it returns false, then you start having problems that you need to solve somehow, and here is the messy stuff that may involve even the operating system. By the way, the good news is, again, spoiler alert, we can use these atomic variables to implement whatever we want. So it's possible to get rid completely of the mutexes. The bad news is that first, it's very, very hard to do it correctly. And second, it's even harder to do it in a way that is really faster than with mutexes. So for some simple cases, you you can do a very good thing. For the others, maybe it doesn't. It's not worth doing. Okay, others. Then I propose I close the meeting here, and if you still have any question, please tell me. I will be available until the end of the allocated time. So thank you and see you next time. Bye.
Thank you. Bye.
Thank you.